I wanted to simulate an entire star system in Unity, and to do that, I basically was going to need to, number one, do research on stars, and number two, I was going to need to actually simulate these multiple different game objects at the same time. And when you have multiple game objects running at the same time, it can be very, very difficult, especially when they're all doing different things at the same time. So, let's get into it. So I started by researching what stars are, and I soon realized that before I could even begin to simulate a single star, I was going to first need to simulate space in a contained way. So I came up with the idea to simulate a pocket of the universe. When we think of space and the universe, we often think of like an empty void filled with planets and stars. But the universe is actually a lot more full than it might appear at first glance. Only 5% of matter in the universe is actually visible to us, but this is actually nowhere near the majority of matter in the universe. Dark matter makes up 27% of the matter in the universe. Scientists believe that dark matter is likely the only thing stopping the universe from tearing itself apart. Okay, so regular matter makes up 5% of matter, and dark matter makes up 27% of matter. But the other 68% is actually something called dark energy. Our universe is constantly expanding at an accelerating rate. This is known as cosmic acceleration. Cosmic acceleration actually distributes dark matter throughout the universe, and it's caused by dark energy. Dark energy causes cosmic acceleration because it has a kind of negative pressure that pushes space outward. However, scientists are still unsure if dark energy even interacts with pressure or any type of force at all. So to simulate this cosmic acceleration, I made a circle and I programmed it to expand outward over time, faster and faster, just like the real thing, except that my version doesn't indefinitely expand. The star spawning system is something I programmed as a prototype for spawning objects. The way it works is that there's a single object, and this object is given a position within the scene where it spawns, and then it's copied, and this repeats for each copy. So let's just run this thing, and wow, that actually worked way better than I thought it would. Some of the objects are spawning on the outside of the circle, but I mean, it technically works. I just need to add some code so that none of the stars would become visible in the scene until they actually got touched by the circle, and now we have a system for spawning objects within the circle. Alright, so now that we have a system for spawning stars, we can actually move on to actually making the stars. But here's the thing, there are actually multiple different types of stars, which all form and function in different ways. Main sequence stars are made up of dust and gas. They're created after this dust and gas spins for over hundreds of thousands of years. So I created a system to simulate gravity, in which the dust and gas would come together when they were within a certain distance of each other. And for the sake of the simulation, we'll simulate time at a much faster rate. So things such as the dust and gas spinning for thousands of years will instead happen pretty much as soon as they come into contact with each other. While this cloud of dust and gas is spinning, it starts to heat up, and inside the core, nuclear fusion begins. In this nuclear fusion, two protons from the center of an atom merge to basically form a helium atom. This fusion is what heats up the star and creates the pressure for it to be born. So I created a system in which, when the space dust and gas was close enough, the process of nuclear fusion would begin, and the star is eventually created. Because objects of greater mass, such as the star, would have a greater gravitational pull on objects like dust and gas, I made it so that the stars would be able to pull in the dust and gas. I created some code so that the camera could move around, and I also created a limit for the number of stars. These stars can last for billions of years, but In our simulation, as you'll soon see, this won't actually be the case. Fun fact, our sun is actually considered to be a main sequence star. Red giants are main sequence stars that are running out of hydrogen or basically don't have any left. Hydrogen is actually the primary gas that stars are made up of in the beginnings of their life cycle as a main sequence star, but over time this hydrogen undergoes nuclear fusion and gets converted into helium. Cyan represents hydrogen, light blue represents helium. I created a timer for each star to keep track of how long they've been in the simulation, and after a certain amount of time, they'll eventually change from a main sequence star into a red giant. If you actually look closely during this transformation, you can see some of the hydrogen convert into helium to represent that this star is low on hydrogen. The core of these red giants will begin to collapse because the energy produced by the nuclear fusion acts as the counterforce to gravity. This results in the core of the star being squeezed, which further increases its temperature and pressure to the point that its helium starts to fuse with carbon, which releases even more energy. Some of this hydrogen fusion migrates to the outer layers of the star, causing the star to expand, and thus the red giant is born. So first, I programmed the red giants to expand up to a certain point. Every red giant will eventually become unstable and start ejecting some of its atmosphere. Eventually, the star's structure will collapse, creating a planetary nebula. A planetary nebula is just a cloud of dust and gas that expands outward. So next, I made it so that after a red giant dies out, a planetary nebula will form. Fun fact, this means that our sun will eventually become a red giant in about 5 billion years from now. A white dwarf is just the core of a red giant that has shed its planetary nebula. A white dwarf is of course smaller than a red giant, but make no mistake, these dwarfs are usually hundreds of thousands of times larger than the Earth. Unlike main sequence stars and red giants, white dwarfs don't actually produce heat, so over time they cool off. White dwarfs can actually emit all kinds of light. They can be red, white, and blue. So to mimic this behavior, I programmed the white dwarfs so that every 2 seconds, every white dwarf would have a chance to change color. Fun fact, in about 10 billion years, our sun will transform from a red giant into a white dwarf. When a main sequence star with between 8 and 20 times the sun's mass runs out of hydrogen within its core, it becomes a neutron star. This made me curious about how mass can impact a star, so I started to do more research and I learned about how mass actually has a lot more influence on a star's life cycle than I initially thought. For example, main sequence stars can only transform into red giants if they're less than 8 times the sun's mass. This meant I was going to need to create an entirely new system that assigned each individual star a mass and used it to determine how the star should transform. For the main sequence stars, I programmed some logic that generated a number. In this case, a number that would be equal to mass between In this case, a number that would be equal to a mass between 1 and 30 would work for now. Then for the red giants, I added some code so that only main sequence stars with a mass that's less than 8 would change into red giants. And finally, for the neutron stars, I added some code for the main sequence stars so that any that had a mass that was between 8 and 20 would change into neutron stars. This resulted in the red giants being much more rare than the main sequence stars and the neutron stars. This actually ended up being more accurate to the actual ratios of stars in the universe, since 90% of the stars in the universe are main sequence stars. Similar to lower mass stars, hydrogen stars will start fusing helium and carbon. Once the core runs out of helium, it will begin to shrink, while also converting its carbon into neon, which releases energy and heats itself up. The star will continue to transform these elements by turning neon to oxygen, oxygen to silicon, and silicon to iron. This process basically keeps the core of the star alive by producing energy while at the same time killing itself, because each new fusion from the silicon to iron means that the star will have less time to exist. Normally, the next step that the star would take is to turn iron into some other element that's heavier, but this would require energy, which the star would already be doing naturally, so by the time the silicon fuses into iron, the star will lose all its fuel in a matter of days. The core of the star will explode, creating a supernova. All that remains will be a neutron star. As the star collapses into itself, the protons and electrons in the star get crushed together into neutrons. If I had to guess, I think that's where the name Neutron Star comes from. So I was basically going to need to simulate a supernova, which hopefully should be easier to do now since I already simulated the planetary nebula, so I made it so that after a certain amount of time, the neutron stars would begin to shrink. And then after it's shrunk down to a certain point, I just increased its size, while at the same time changing its animation and setting it back to its default size. Just with a smaller sprite to show what a supernova would look like. After the star explodes, all that's left is basically just a super dense neutron star. Pulsars are a type of neutron star. They get their name from the fact that they have pulses of radiation which form on the surface of these stars, and they're actually hotspots for radiation, which can range from seconds to milliseconds, and these happen at regular intervals. Pulsars act similarly to a lighthouse in that they emit beams of light which sweep across space. We can observe this better when one of the star's lights is angled in a certain way. So to simulate this, I created an animation for the pulses, which incorporated these beams of light and had them rotate slowly. Magnetars are easily my favorite types of stars. They kind of look like a celestial is about to break out of them or something. Magnetars are stars that are extremely magnetic, and they're covered in a shell, which is made up of magnetic material, and it's all being locked in place by the magnetic field of the star. And because the star's magnetic material is under an insane amount of strain, even a small movement in the crust could be highly explosive. If an explosion was to occur, it would release large amounts of electromagnetic radiation, which also ripple throughout the magnetic field of the star. A magnetar's gravitational pull can be 10 trillion times stronger than a refrigerator magnet. So to replicate the magnetar's insanely powerful magnetic pull, I programmed each magnetar to have over double the pull radius of every other star in the simulation, and also gave it the strongest pull value out of all of them. This isn't exactly how it works, but for the sake of the simulation, I did this to represent that the magnetars have a stronger magnetic field. The next thing I needed to do was to replicate the magnetar's outer crust. Some space dust is actually made up of magnetic material, and because this outer crust forms because of the magnetar pulling in magnetic material, I made it so that when the magnetar comes into contact with the dust, the amount of crust on the outer layer of the magnetar increases. Once the magnetar has collected 2 clusters of space dust on its outer layer, its outer shell will be complete. And for the purpose of the simulation, I made it so that the inside of the magnetar would still be visible. After that, I needed to create a system to simulate the magnetar's magnetic shockwaves. So I created a system so that every 3 seconds, the magnetars had a 50% chance of having a magnetic shockwave, which had an equal chance to occur on the top, bottom, left side, or right side of the Magnetar. After I finished all the code for the Magnetar, I observed an interaction where one of the clouds of cosmic dust would basically get stuck between two stars, even though the dust was very clearly closer to one star. This made me realize that the way gravity worked in the simulation was pretty basic and not really the best. So I began researching to understand how gravity actually influences different objects in space. If something has mass, that means it also has gravity. The more mass something is, the more gravitational force it can exert on other objects. Gravity gets weaker with distance, which means that objects that are closer to each other have a stronger gravitational pull, and objects that are farther away from each other have a weaker gravitational pull. The way it worked in the simulation was that each star would have a pulling value, which would then determine how fast it could pull in other objects, but gravity doesn't really work this way. Let's say object A is pulling object B, and object B is also pulling object A. Typically, they wouldn't just move towards each other at the same speed. The closer object A and B got to each other, the faster they would move together because their gravitational pull on each other would be stronger. And also, if object A was a very significantly larger amount of mass, like the mass of Earth, and object B was a very significantly lower mass, like the mass of like a pencil or something, even though both objects are exerting gravitational force on each other, because the amount of force object B is exerting on object A is so much lower in comparison to object A, object B would be pulled. So to fix this, I created some logic to calculate the distance between objects, and depending on how close an object was to another object, it would have a weaker gravitational pull or a stronger gravitational pull. Red dwarfs actually look more orange than red, and they make up about 75% of the stars in the Milky Way galaxy, but because they're so faint, they're really hard to see even in the night sky. Red dwarfs are the smallest and the coolest types of main sequence stars, with a surface temperature of 2,500 to 4,000 K. Red dwarfs can have 0.08 times the mass of the Sun to half the mass of the Sun, so 0.5. So to start, I already had a system that simulated each star's mass. I only needed to alter the chance that a star's mass could end up between 0.08 times the mass of the Sun and 0.5 times the mass of the Sun, since that's the range in which a main sequence star would be considered a red dwarf. I already knew that around 75% of stars in the Milky Way galaxy are red dwarfs, so I programmed the simulation so that there is a 3 in 4 chance that a main sequence star has a mass between 0.08 and 0.5, which means that there's also a 25% chance that they could end up as a non-red dwarf main sequence star by having a mass that's over 0.5. And just a reminder that mass and size are not the same thing, so even though it might look as though this red dwarf star and this main sequence star have the same mass, they of course don't. After coding the logic for the red dwarf, I observed a pretty cool interaction that happened in the simulation, where a red dwarf star formed because of a magnetar that had pulled in a cloud of gas and a cloud of dust together, close enough to form a red dwarf star. This actually isn't accurate, since gas and dust that's already being pulled in by a star isn't going to form an entirely new star in most cases. However, the next type of star is technically the exception. The first time I saw a brown dwarf, the first thing I thought was, how the heck is that supposed to be a star? And well, brown dwarfs aren't quite as big as a star, and they aren't quite as small as planets, which means that they aren't technically stars and they aren't technically planets, which lands them in this kind of gray area. The reason why fusion doesn't occur in brown dwarfs is because they never really reach a high enough mass to do fusion on the same level or scale as a main sequence star. Stars have over 80 times Jupiter's mass, but most brown dwarfs have between 13 and 80 times the mass of Jupiter. Brown dwarfs basically don't emit any visible light. However, some scientists have seen some with an infrared or electromagnetically radiated light. Adding in brown dwarfs was going to be a little bit different from adding in any other star, because even though brown dwarfs can form like main sequence stars, they can also form like planets. Because brown dwarfs can form near other stars similarly to planets, I ended up using the same system I already made to calculate the distance that each gas cloud and dust cloud was from a star. Then I just made it so that if a cloud of dust and a cloud of gas interact while being pulled in by a star, that instead of becoming a main sequence star, they would instead become a brown dwarf. Next, I need to figure out the ratio of non-brown dwarf stars and brown dwarf stars in the universe, or at least an average equivalent to this. By knowing this, I would be able to know how common they are in the universe and how likely they were to form using the same method as a main sequence star. Within 32.6 light years of Earth, only 12 brown dwarf stars have actually been discovered. And we can compare that to the 239 red dwarf stars that were also discovered within that same 32.6 light year range. And we can make an equation like this. Then we can simplify this by dividing 239 by 12 to get, well, this number. So we can assume that for every brown dwarf there will be around 20 red dwarfs. So I made it so that there was a 1 in 21 chance that a star formed within interstellar space could be assigned a mass less than 8% of the sun's mass, which is equal to 80 times the mass of Jupiter, and greater than 0.013 times the mass of the sun, which would make it a brown dwarf if it was not a non-red dwarf main sequence star. Because brown dwarfs are smaller than stars, I decided to decrease their scale to be 0.7 of what a main sequence star would be. And there's one more thing I wanted to include to the brown dwarfs. So you might have noticed this fiery looking ring that can appear on some brown dwarfs. This is called an auroral display. Auroras on Earth are much dimmer than the ones that appear on brown dwarfs. When charged particles enter the Earth's magnetosphere, they collide with the atoms of the gas which results in an auroral display. Radio emissions are produced when the electrons spiral down towards the atmosphere. Once these particles hit the atmosphere, they cause the hydrogen to react. This auroral behavior is of course not limited to Earth. There's something that can be observed in other planets and brown dwarfs. On Earth, these auroras are more green, but because a brown dwarf's atmosphere has significantly more hydrogen, its aurora is a more fiery red and orange. So I got started on making the system to simulate these auroras. The main difference between the code for the magnetar shockwaves and the code for the brown dwarf's auroras is that the magnetar shockwaves would only have a chance of happening between 3-second periods / intervals, while the brown dwarf's auroras would have a chance of happening between 9-second period intervals. After doing research on SMVs, it definitely made me realize that I have millenioheliophobia, the fear of black holes. When a main sequence star with over 20 times the mass of the sun runs out of hydrogen, it becomes a stellar mass black hole. If I had to give you the simplest definition of a black hole, I would tell you that it's an object that is so extremely dense that not even light itself can escape it. And you might be thinking, if stellar mass black holes are so powerful that light can't escape them, then how the heck are we able to see them? And well, that's the thing. We actually can't. The study of black holes relies very heavily on indirect detection. So even though astronomers can't actually see black holes, they can observe how other objects are reacting in a way that could be an indication of the presence of a black hole. Every object has a Schwarzschild radius, which is the radius at which a mass has an escape velocity, equal to the speed of light. An escape velocity is the speed that an object needs to have to escape another gravitational attraction. An object that's smaller than its Schwarzschild radius is considered a black hole. Stellar mass black holes have such a strong gravity that they're actually able to pull the gas away from other stars. When colliding with other stars and even other black holes, they actually gain mass. The average stellar mass black hole weighs between 5 and 10 times the sun's mass. So I started by making it so that every main sequence star with more than 20 mass would eventually become a stellar mass black hole. Then I copied some of the code I used for the other stars to simulate gravity and increased the value so that they would have a significantly stronger gravitational pull compared to every other object. I also gave them the ability to pull in and destroy other stars. And even after doing extensive research on how black holes work, I still can't look at an image of one for too long. Stars are held together by two main forces, gravity and heat. The gravity of the star's core pulls the material inward, and at the same time, the heat from the star's core creates pressure which pushes the material outward. These are the main forces that balance a star. Stars cool off after they run out of fuel, and when this happens, the pressure drops, which then results in an expanding cloud of dust and gas. The first thing I changed was a bit of code for the dust clouds, because before, when the dust clouds came into contact with gas clouds or stars, they would basically be deleted from the simulation. So instead, I just had them become invisible. And then I made it so that once a star became a supernova, that the dust cloud would be ejected from the star. When a dust cloud is being ejected, it's too heated to be able to form a new star, but it's still able to be pulled in by an already existing star. So now that we have this code for the dust clouds, we can pretty much just copy this and use it for the gas clouds, and everything should work perfectly. Bruh. There was an issue where the stars would keep ejecting dust clouds, and I was able to fix this pretty easily, but it did give me a good idea. Originally, I was going to have the supernova only eject a gas and a dust cloud, but I realized that ejecting multiple lower mass dust clouds and gas clouds would be more similar to the expanding cloud of dust and gas that can be observed as a result of a supernova. This is my first attempt where I had no limit on the amount of ejected objects. And here's my second attempt where I limited the number of ejected objects to 4 and made it so that each ejected object would have an equal chance of being a gas or a dust cloud. Fun fact, the iron in your blood can actually be traced back to cosmic explosions such as supernovae. And yes, it's supernovae, not supernovas. Which means that supernovae are essential to life. So I guess technically, we're all part star. Alright, so I learned a lot about all the different types of stars. I learned that stars are made up of this dust and gas, which, accumulates and stuff. So that's pretty cool. I learned about, all the different types of stars. I didn't know there were types of stars. So that's pretty cool. I also learned, I also have a new fear now. So there's actually three things. So I have a new fear now of millennial heliophobia. And yeah, that's pretty much it for now. And if you want to support the channel, be sure to like the video. If you want to, see more stuff like this, be sure to subscribe. If you want to, give a specific request of a type of video you want to see, or video format, or whatever you want to see, you can comment that in the comments. Yeah, that's pretty much it for now. And I hope to see you guys in the next one. Alright, very cool.